Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, welcome back. AP Physics 1. We're in Unit 5, Torque and Rotational Dynamics. This is the second video. The first one we talked about angular displacement versus displacement linear displacement. And we talked about how that angular displacement is measured in radians. We talked about direction, counterclockwise is positive, clockwise is negative. And we talked about what angular displacement it is. It's just how far around it got when it was spinning on its axis. All right, did it get around 1 revolution, 360 degrees, or 2 pi radians? They all mean the same thing, right? It's just a different way, like feet, meters, centimeters, different way to measure the same thing. We gotta have it in radians though. We also talked about not abbreviating radians as R, abbreviated as rad, because rotational dynamics is rad. All right, now we're gonna be talking about velocity today, so let's get started. That was a quick overview. Let's get started. Our linear, we're gonna compare linear with angular, because I'm telling you, after teaching this for 10 years, I just felt like, and the students said they get it better if they can compare it to something they already know. Okay, so velocity, the symbol is a V, we know this. The unit was meters per second. Why? Because velocity was the change in that displacement over time. So meters is displacement, time was seconds. Now let's go to angular velocity. Before we talk about angular velocity, let me give you a little demo here of what it is. Just like when we talked about velocity being the displacement, like of a car going down the road, from point A to point B, that the meters between point A and B divided by how long it took you to get from point A to B, because it's a rate. So that was your displacement in linear. Now we're talking about angular displacement. So that means if I go 1 revolution or 2 pi radians, if I do that really slow, then you're going to have a slow angular velocity. Just like if you do that really slow from point A to B in a car, really slow, you have slow velocity. But if you do it really fast and get 2 pi radians in a very short time, you're going fast. Your angular velocity is high, just like when you go point A to B in a car in a very fast time, then you have high velocity. So really what angular velocity is, just like in a car, it's about how fast it's going. In angular or rotational dynamics, it's about how fast is it spinning on its axis. Is it going really slow or is it going fast? Okay, that's angular velocity. Now that we know that, let's go through the symbols. Remember, it's all Greek. There are a lot of Greek letters here. The symbol is a lowercase omega. All right, just like how the English language has uppercase and lowercase letters, so does your Greek alphabet, and this is the lowercase omega. The unit, well, the equation, just like how velocity was displacement divided by time, so is angular velocity. It's just angular displacement over time, which was the symbol delta theta. So guess what? Just like how velocity, the displacement was meters, time was in seconds, so it was meters per second. Angular velocity, our displacement was measured in radians, and over time is seconds, so it's radians per second. Okay? So if we went around 1 revolution, that would be 2 pi radians, and we did that in 1 second, then it would be 2 pi radians divided by seconds. If we did it in 2 seconds, then it would be 2 pi radians divided by 2 seconds, or pi radians per second. All right, if you did 2 pi radians divided by 2 seconds, your 2's cancel out, and you'd have pi radians divided by a second. Perfect, so that's what angular velocity is. Your direction is still the same. Remember, counterclockwise, and I'm going to do counterclockwise like that, is positive, clockwise is negative. Now, I recognize that the right hand rule is really the way to do that, because depending on which side of the rotational axis you're on, it could look different. But for AP Physics 1, we keep it to this. AP Physics C, you're going to learn how to use that right hand rule, and then you'll continue using that in your engineering curriculum. Been there, done that. All right, so tangential velocity. Let's talk about tangential velocity for a minute. We're going to have another kind. We had linear velocity, we have angular velocity, But now we're going to talk about one more type of velocity, and that's tangential. All right, so let me give you a example here. I've got a car. I used to work for Chevron as an engineer. This is a Chevron car. If you're from the West Coast, you may be familiar with some of these. But anyway, we have, by the way, two of our friends, my husband and I's friends, were on the design team for these cars, so shout out to them. Great job. The wheels on this car go round and round, and in fact we had that kids song when we were little and preschool. The wheels on the bus go round and round. True, they do, but the bus or the car in this instance goes in a straight line. It has linear velocity because the wheels are spinning. All right, so because there's angular velocity and these wheels are spinning, then there is linear velocity. And the faster the wheels spin, the higher the angular velocity. The faster the spin, the faster the tangential velocity or linear. The slower they spin, or the lower the angular velocity, the lower the tangential velocity. So we like to call this, instead of just linear velocity, we like to call it tangential to recognize that this is linear velocity due to rotational motion. Or, if you want to say, or angular velocity. They are dependent on each other, okay? So wheels on the car go round and round, car goes down the road. On your bike, your wheels go round and round, but you and your bike don't go round and round, hopefully, if there wasn't a fall, but your bike goes down the road. Same thing with skateboards, same thing with trucks, trains, you name it. But it's a linear velocity that is due to the wheels turning. All right, so the symbol for this, let me switch colors again to stay consistent. The symbol is VT. It's just like linear. It's just linear velocity. We think of like a block with no wheels that just slides across a surface or slides down a ramp. All right, that's linear velocity. And then we have angular velocity. How fast is it spinning? And then we have tangential. It's just how fast is it going down the road due to that angular velocity, okay? Now, the unit is the same because it's really just like linear velocity, so the unit is meters per second. Now, the equation is different because it's due to rotational motion. So the equation has to be tied to rotational motion. So the equation is tangential velocity equals the radius times the angular velocity. This is why you don't want to abbreviate rads as r, because you're going to see a couple of equations here with r in it. So in other words, if I am going, as I just demoed, if these wheels are spinning slow, and it's a small angular velocity, because they're not spinning very fast, then my tangential is also going to be, that linear velocity is also going to be slow. And by the way, that is tangent to those wheels. That's why it's called tangential velocity. All right, if I got bigger radius, if my radius went up, then my tangential velocity is going to increase. If my spinning, how fast it spins, or this angular velocity, if it goes fast and we increase that, also my tangential velocity increases. So that is the difference between tangential, angular, and linear. And hopefully you understand that all well. Now I'm going to do one concept question they love to ask, and it's great for you to understand, to test your knowledge. I'm going to be like a drone, and I'm looking down on a carousel. All right, I've got a horse A here, and I've got a horse B here on the edge. All right, I was just in Germany at the Christmas markets. There was a beautiful carousel there in Germany. So let's pretend we're there, and we're at a drone looking down on this carousel. The question is going to be, compare A and B's angular velocity. How fast are they spinning? All right, and the two horses, A and B's horse, tangential velocity. Okay, they want you to compare those. Okay, first of all, you know on a carousel, these two horses are welded to this metal plate. They're not on a separate track where A can like just keep over, like can keep lapping B and moving faster than it can, right? So they're on a welded plate. So they both get around 2 pi, which is, right, one time around, one on the axis, one complete turn on the axis here, 2 pi radians over, let's say it's, well, I don't care. We can say it's 2 seconds. That would be a very, very fast carousel. All right, but actually let's not do that. That would be way too fast. Let's say we do it in, I don't know, 30 seconds. All right, so we have, it goes 1 time around, both of them, because they're both on, like, welded on. This one cannot overlap B. All right, so they both make the same turn in exactly the same time. Kind of like no matter where you are on the earth, you're making one rotation in 24 hours. Basically 24 hours, right? So, but you're making one rotation our day is based on making it around once in 24 hours. Okay? Now, let's talk about, now it's different if you're at the poles or the equator, that's a whole nother issue we will talk about in these units coming up, that what that does. But anyway, so now we're going to talk about, and we can actually talk about it now, your tangential velocity. So which one, so in other words, A and B are equal. So A and B's angular velocity, and I'm going to write that up here, A and B's angular velocity is the same, because they both go 1 revolution in the same amount of time. Okay? Now though, what about the tangential velocity? Which one, compare A and B's tangential velocity, are they the same? Remember, tangential velocity is radius times the angular velocity. Okay, well let's say that B is 2 meters. So this radius of this whole rigid metal plate is 2 meters. A is at 1 meter. All right, well look at this. For tangential velocity for B, it would be 2 is the radius times the angular velocity, which is the same for both. But for the tangential velocity for A, the radius is 1 times, they both have the same angular velocity. They both get around 2 pi radians in 30 seconds. All right, so guess which one has the biggest tangential velocity? It's B. So the tangential velocity of B is greater than the tangential velocity of A. Double, actually. This is 1, this is 2. All right, why is that? Okay, well, let's think about it. If they're both getting around 2 pi radians in 30 seconds, that means B has to go all the way around in 30 seconds, and A just has to go there in 30 seconds. All right, so B has a lot farther path to travel in the same amount of time. It'd be like if I asked you to go to your kitchen in 30 seconds, and then I asked you to go to the end of the block in 30 seconds. You're gonna have to be moving faster. Your linear velocity is gonna have to be faster getting to the end of your block in 30 seconds versus your kitchen. All right, so same thing here. So horse B has the greater tangential velocity because it's got a lot farther to travel in 30 seconds. A has the less tangential velocity because it does not have as far to go in 30 seconds. But yet they both have the same angular velocity because they both go 2 pi radians in 30 seconds. It's very similar to the Earth. If you're on the equator, the Earth is bulky in the middle. All right, it's bulky in the middle. Somebody living at the equator has to get all the way around that part of the Earth in 24 hours. Somebody up by Alaska that's close to the axis, maybe they have a little bitty path they have to go in 24 hours. Both of them have the same angular velocity. They're both making 1 revolution or 2 pi radians in the 24 hours. But the one on the equator has to be traveling a lot faster. And that is exactly what happens for their tangential velocity. Okay, now you get it. I hope you understand that. I hope you understand the difference between velocity and angular velocity. Spend some time with these units and symbols because that's going to help you feel a lot better about this unit. All right, thank you for watching. I hope you enjoyed this. If you did, please like it, share it, subscribe. We'd love to have some feedback. And thank you very much and happy physicsing.